Alright, I've got this working a bit better. What I've done now is I've put my own primary coil on that. Nice wire. And it runs on 24 volts this. So the problem with the tiny arcs last time was I was using the internal primary, which was normally meant for like 180 volts, like they run off like direct mains in the TV or whatever. So yeah, I'm going to plug this in now. There's the wave, and there it's 24.1 volts. So when you arc, it would actually go lower. So it's not actually really running on true 24 volts, but look at how powerful this is. I should probably actually be using a chicken stick, but because this is ground, it's not actually grounded, but it's not, yeah. That's like having a ZVS on 36 volts. Oh, that's almost like having a ZVS on 36 volts. That's really red arc. Said I wasn't going to do, yeah, it's actually not red, it's orange. Well, it's actually like white, more like white. But very comparable to a ZVS. I can do an arc now. That's running at about 22 kilohertz. Okay, I'm going to arc this for a long time on purpose to test how warm the fullbridge will get. But you know those two channels, I'll put them in parallel, so when I'm running the Tesla coil I could put them in parallel if I'm running it up to 36 volts. But if I want to go higher, then yeah. But this, there is a, you can hear a 60 hertz hum in this because it's drawing current, bit of current. Actually, let's have a look at how much current this is drawing. Voltage drops to, well, it's 23.7 volts, drops to 21.3. Well, this is going to be the last arc. Alright, let's put that there on top of the screwdriver. And turn the variac right down. And now we discharge the flyback transformer. And fill the heatsink. Heatsink is only a little bit warm. It's not very warm at all. It's like comfortably warm. So I don't know what you could compare this to, but it's just comfortable warm. Like you could hold on to this all day and warm up your hands, but it's not going to burn you. This side, and it's all nice and cool. Heatsink for the regulator. That's nice and cool. These are tiny weeny bit warm, but most of the heat is coming out those heat sinks, so that's good. It's being efficient. These transformers, they're a little bit warm. The oscillator IC is stone cold, so that's excellent. Plus, these heat sinks are only a tiny bit like they're comfortably warm. I could keep them stone cold, like below stone cold, if I turn this fan on because it's so powerful. So imagine the amount of power I could put through it. But the transformer, the power is limited to 1000 watts with that transformer. So yeah, but I think 1000 watts through that Tesla coil would be enough for a bit of fun. So yeah, that's going to be very cool. What I need to do is I need to gut it and get the guts out of the previous thing, 10,000 volt capacitor. I need to get the spark gap out, I need to get the fan out, I need to get that high voltage 10,000 volt transformer out, but there's lots of space down here, so I could try and put a lot of stuff here. The only problem is the wheels. They'd probably like dig all the wheels into the floor. So yeah, and normally I don't push it along all the time. So carrying it's going to be an absolute pain if it's going to have about 2,000 watts of transformers in it, and then there's another like 1,800 watts here, but that's not going to be inside the thing, of course. Right, let's fill these transformers. That transformer's just a tiny bit warm. This transformer that was powering it is stone cold. Variac's a little bit warm because it's been on all day. This transformer powers a lot of that. It powers all of the low power circuitry. It does. Cause this transformer goes like the output of this goes to the oscillator circuit and then the fan through the regulator, of course, and but the output of this, the AC output of this, before it gets rectified there, goes to this, and then this steps it up to 150 volts, which goes into these transformers, which then comes out as 18 volts DC after the rectifiers, and then goes into these. So like that's all the low power circuitry, like gate drive stuff, all powered by this. And then this is going to be the like main power supply inside it. Let's feel the heat sinks. I could tell which channel I was using. It was this channel here with this rectifier, because that's the warmer one. It's only a tiny bit warm though, so that's great. The warmest thing here is actually the oscilloscope, because it's really old. It gives off a lot of heat. Transformer in the back is quite hot. Yeah. Plus you can't actually put your hand inside that and feel the resistors and stuff inside there, so they're probably even warmer than like the casing. Of course they're warmer than the casing, but yeah, this is bare bones stuff, so that's good. But advantage over a ZVS is if you touch both these heatsinks at the same time, you won't get zapped, because it's not AC, it's DC across these two, and so this DC across these two will be equal to the input voltage. So because I've basically used each heatsink as a bus bar for the positive and negative rail. So this one's negative and that one's positive, and then there's the insulator in the middle, which is the fan, and then the fins are pointing inwards to the fan. So yeah, I think that's about it. Let's see if this alligator clip's cold. Yeah, it's cooled down. Flyback transformer probably got warmer. Actually, yeah, the flyback transformer got warmer than anything else, because yeah, right now it's about as warm as the heat sinks were when I first touched the heat sinks. So that flyback transformer was probably quite warm when I was doing that. So yeah, this thing is nice and beastie. Yep, see you in the next video.